Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to discuss on probability. Yes, so no doubt you are familiar with terms such as probability or chance and likelihood. So they are often used and of course, interchangeably they have been used previously. A probability is frequently expressed as a decimal, such as 0.02, 0.05, or 0.027. So, however, it may be given as a fraction, such as if I just want to specify 0.7, of course, it is 7 divided by 10. If I just want to specify as like 0.27, yes, of course, it can be as like 27 divided by 100. So, it can assume any number from, yes, exactly, dear friends, 0 to 1 inclusive. If a company have any 5 sales regions and each region's name or number is written on a slip of paper and the slips put in a hat, the probability of selecting one of the 5 region is of course 1. The probability of selecting from that hat a slip of paper that reads any further location, X location, that's we don't know. When we just picking, we don't know. And that exact X location, yes, it is obviously 0. So thus, the probability of 1 represents something that is certain to happen, and the probability of 0 that represents something that cannot happen. So the closer a probability is to 0, the more improbable it is the event will happen. And dear friends, the closer the probability is to 1 and more sure we are it will be. That is what we just read. It will be happen. And dear friends, there are 3 keywords are used in study of probability, that is experiment, outcome and events, and these terms are used in our everyday language. But in statistics they have specific meaning. Yes, this exact definition is more general than one used in a physical science, or where we picture someone manipulating test tubes or microscopes. In reference to probability, an experiment has 2 or more possible results and it is uncertain which will occur. So of course, experiment, that is what we often going to use it here. And next, it's outcome, particular results of an experiment. So for an example, if we are having this exact dice, okay, so let me just toss a coin as an experiment, or we just have any die to be tossed. So see, if you just making it as like a coin, so you may observe the toss of a coin, but you are unsure whether it would be head or tail. Okay, so if the coin is tossed, one particular outcome is head, the alternate outcome is tail. When one or more of this experiment occurs or observed, we call it as like event. Okay, now let me just have it here. So in a die, let me just rolling it. Okay, so this experiment, let me have this. There are 6 possible outcomes when we just roll a die. So observe it, 1, 2, 3, 4, 5, 6. Okay, but there are many possible events. Kindly just make sure there would be many possible events. That is, you can just say that is observe a number greater than 4, observe a number 3 or less. So these are all possible events. And here one more example, when we just taking when we counting the number of members of a board of directors. For an example, if we just take it for a Fortune 500 companies who are over 60 years of age. So the number of possible outcomes can be anywhere from 0, okay, so from 0 to total number of members. There are an even large number of possible events, okay, so that is in the experiments. So just lightly have it, dear friends, what is the difference between this, or what are all these terms we are just going to make use it in our probability functionality. And when we just approach to make or approach to making towards an assignments, see, two approaches to assigning probability to an event will be discussed, namely, yes, the objective and the subjective. And when coming towards this objective, yeah, this classical probability is one among the subdivided category. And here, classical probability is based on the assumption that the outcomes of an experiment are equally likely. Yeah, using a classical viewpoint, the probability of an event happening is computed by dividing, yes, kindly just observe, by dividing the number of favorable outcomes by the number of possible outcomes. So consider here, if I just want to make it one, just rolling the same thing, rolling a six-sided die, what is the probability of an event? An even number of spots appear face up. There are three favorable outcomes. That is, if you just taking us like an outcomes, yes, you can just have 2, you can just have 4, and 6 is a collection of 6 equal likely possible outcomes. So here, if you just take it towards that particular manner, so the probability of an even number, here it would be 3 among the 6. And here what would be the outcomes? Yeah, here it is the 0.5 would be the probability of an even number. And here, yeah, dear friends, one more concept, that is mutual exclusive concept, appeared earlier in our session of frequency distribution. We have already discussed. Let me just recall that we create a class so that a particular value is included in only one classes, and there is no overlap between the classes. So thus, only one of several events can occur at a particular time. So that's specified as like a mutual exclusive. Here, for an example, if I just want to specify a gender, okay, so gender, so the variable gender presents mutually exclusive outcome. What would be the outcome? Yes, male and female. An employee selected at random is either male or female, but cannot be both. Okay, one more example, let I just make it. So a manufactured product, any parts, any parts or spare parts or any other thing, one is acceptable or unacceptable. So the part can be both acceptable and unacceptable at the same time. In a sample, how come you just make it this? So in a sample of manufactured parts, the event is selecting an unacceptable parts, and the event of selecting an acceptable part are mutually exclusive. And if an experiment has a set of events that includes every possible outcomes, such as, yes, as I have already specified here, events an even number and an odd number. So in a die tossing experiment, then the set of events in collective exclusive, what would be? Yes, for the die tossing experiment, every outcome will be either even or odd. So the set is collectively exhaustive. So at least one of the event must occur when one experiment is conducted. Okay, so that is what collective exhaustive. And if the set of event is collectively exhaustive and events are mutually exclusive, yeah, the sum of probability is 1. So it is unnecessary to do an experiment to determine the probability of an event occurring using this classical approach, because the total number of outcome is known before the experiment. Okay, yes, let me just move on to empirical. So this is also one among the objective probability. Yes, dear friend, here this empirical probability, or otherwise specified as like a relative frequency, is the second type of objective probability. It is based on the number of times an event occurs as a proportion of a known number of trails. So here, in such a case, if I just want to specify an empirical probability, yes, number of times the event occurs is divided by total number of observation. Here, the empirical approach to probability is based on what is called the law of large number. So the key to establishing probability empirical is that more observation will provide a more accurate estimation of a probability. So that is here it is specified the law of large number. Yes, dear friends, to explain the law of large number, suppose we toss a fair coin. The result of each toss is either a head or a tail. With just one toss of a coin, the empirical probability for head is either 0 or 1. If we toss the coin a greater number of times, the probability of the outcome of the head will approach 0.5. That's so here, we have just specified a demonstration here. Kindly just observe. Based on the classical definition of probability, the likelihood of obtaining a head in a single toss. Number of head, we don't know. Okay, but towards a fair coin, it would be as like a 0.5. Based on this empirical or relative frequency approach to the probability of an event happening that is approaches the same value based on the classical definition of the probability. So this reasoning allows us to use the empirical, that is relative frequency approach to finding the probability. Next, let me just move on to subjective. Dear friends, if there is a little or no experience or information on which to base a probability, it may be arrived at subjectively. So essentially this means an individual evaluates the available opinion and information and then estimates or assigns the probability. So this probability is aptly called the subjective probability. And as I have already specified, the likelihood of a particular event happening that is assigned by an individual based on whatever information that is available. And to illustrate this, we have so many examples as like estimating the likelihood the New England Patriots will play in the Super Bowl next year, like that. Or estimating the likelihood you will be married before the age of 30. That is also a subjective. So in such a way, what is that age of 30? Yes, the information that is available. Okay, yes, next, I just want to give you a small summarization what we have discussed now. Yes, dear friends, the types of probability are summarized here. A probability statement always assigns a likelihood to an event that has not yet occurred. So there is of course a considerable latitude in the degree of uncertainty that surrounds this probability based primarily on the knowledge possessed by an individual concerning the underlying process. So here the individual possesses a great deal of knowledge about the toss of a die and can state that the probability that one spot will appear face up and the toss of the true die is 1/6. But we know very little concerning that acceptance is in the market of a new or untested product. Or for an example, say even though a market research director tests a newly developed product in a something as like 40 retail stores and states that there is 70% of chance that the product will have sales for more than 1 million units. Here, okay, he has a limited knowledge of how consumer will react with it. It is marketed nationally. In both the case, that is the case of person rolling a die and the testing of a new product, Here, the individual is assigning a probability value to an event of interest, and difference exists only in the predictor's confidence is the that is prediction of the estimation. However, regardless of the viewpoint, the same law of probability will be applied. Okay, so yes, some rules for computing probabilities. Dear friends, now that we have defined probability and described the different approach to the probability, we turn our attention to computing the probability of two or more events by applying rules of addition and multiplication. Here, coming towards these rules of addition, yes, there are two rules of addition: the special rule of addition and the general rule of addition. And we begin first with the special rule. Okay, so here this special rule, to apply this special rule of addition, the events must be mutually exclusive. Kindly just observe, it should be mutually exclusive. Recall that mutually exclusive means that when one event occurs, none of the other event can occur at the same time. As we have already illustrated, see, actually of a mutual exclusive event in a die tossing experiment, if a number larger than 4, okay, number 4 or larger, and one more event, number 2 or smaller, this is 4 or larger, this is 2 or smaller. I am just having two outcomes, two events. If the outcome of this group, this event 1, what would be? Of course 4, 5 and 6. This would be the set of the event for this. And then it can also be in the second as like 1 and 2. So if this two event A and B are mutually exclusive, the special rule of addition states that the probability one or more or one or the other events occurring equals the sum of this, sum of their probability. So here what would happen? When I just want to add this both event 1 and 2, yeah, I just get 1, 2, 4, 5 and 6. And here, if you just have event A, B and C, yes, of course, dear friends. So, if for 3 mutually exclusive events that is designated as like A, B and C, yeah, how the rule would be written? Yes, of course, A or B or C, that is the probability of an rules of addition. Here it would be probability of A plus probability of B plus probability of C. Okay, so this is how you can apply. And next it is all about complement rule. See, the probability that a bag of mixed vegetable selected is underweight. Let me just take it, P of A. Plus the probability that is not an underweight bag, that would be complement of A. So, and actually it is read as not A. If I just make the summation of both, yeah, must logically equal to 1. And how it has been written? Yes, of course, P of A plus P of not A, which is equal to 1. And when you just make it towards the complement rule, see, actually this is the complement rule, that is it is used to determine the probability of an event occurring by subtracting the probability of an event not occurring from this. So that is how it would be calculated. This rule is useful because sometimes it is easier to calculate the probability of an event happening by determining the probability of it is not happening and subtracting the resulted from 1. So here that notice that an event, if I just have for an example, yes, this is an towards an probability, that is which we just say a probability that has a sum of 1, so 0 to 1, and here I have a probability of A That is an event A. And what would be the other one? Yeah, it is a not A. So notice that event A and this not A are mutually exclusive and collectively exhaustive. Therefore, the probability of A and not A would have the sum of 1. And yeah, this exact diagram would just illustrate the complement rule. It is exactly shown as P of A. If I just want to calculate P of A, I can just subtract it from 1, which is not A. Okay. So that is how this complement rule would works. And yeah, next coming the general rule of addition. Dear friends, here the outcome of an experiment may not be mutually exclusive. That is what the main thing. That is not mutually exclusive. And here the same. However, that this probability cannot be greater than 1. That is also kindly have a note on to it. And I just want to specify it with an example. So if I just want to go towards this, just keep it in mind this particular rule. That is, if I just going not and mutually exclusive, yeah, I have to add upon with two event, that is designating A and B here. Yes, A, probability of A plus probability of B, and added towards, subtracted towards probability of A and B. So for this, the word or here the suggestion that A may occur or B may occur, this also includes the probability that A and B may occur. And if I just want to show how this happens, see here, let me just have, suppose for an illustration, here of course the Florida shows having a selected of a sample of 200 tourists who visited the state during that year. Okay, here the survey revealed that 120 tourists, okay, among 200, 120 tourists went to Disney World. And 100 went to that Busch Garden. That is near Tampa. So that is Busch Garden we went. And next, of course, what is the exact probability that a person selected visited either Disney or to that garden? So if the special rule of addition is used, the probability selecting a tourist who went to Disney, it would be 60. That is 0.6 probability, that is founding it by 120 divided by 200. And similarly, the probability of tourists going to the garden, it would be that is 0.5. Then the sum of these probability, it would be just, if I just add it, what it happens? I just get 0.50, it would be 1.10. And we know, however, that this probability cannot be greater than 1. So the explanation is that many tourists visited both attraction and are being counted twice. So a check of survey response revealed that this 60 out of 200 did in fact visit both attraction, that is both places. So in such a case, so to our question, so what is the probability? A selected person visit either Disney World or this Busch Gardens. So here, of course, first add the probability that the tourist visited to this Disney and add it probability that they visited the garden and subtract the probability of visiting both. So if you just make this, yeah, here we just get 0.80. And yes, dear friends, when two events both occur, the probability it is specified as like a joint probability. So that we have specified here. If we are adding this A and B, that is a joint probability. And yes, with this joint probability, we are, that is the probability that the tourists visit both the places is an example here. It is specified. And by using this illustration, we have just specified this Venn diagram. So kindly just have a look. That is two events that are not mutually exclusive. If it shows that two event overlaps here, illustrating the joint event that some people have visited both the things. And yes, dear friends, to also include this, combination of, yes, if I just want to specify A or B, what happens? How come? May occur or may. Maybe A may occur or B may occur, like that. So yes, this also includes the probability that A and B may occur. But here the use of this or is also sometimes called inclusive. Okay, you could also write A or B or both. So to emphasize that the union of an event includes the intersection of A and B. So if we compare the general and special rules of addition, the important difference is determining if the event are mutually exclusive. Okay, so if the event are mutually exclusive, then the joint probability P of A and P of B, that is here P of A and B is 0, and we could use the special rule of addition. Otherwise, we must account for the joint probability and use the general rule of addition. So kindly just have both the difference, where to use which one. Okay, and let me just have the rules of multiplication. Yes, dear friends, the rule of multiplication. When we used the rule of addition, we found the likelihood of combining two events. And in this discussion, we find the likelihood that two events both happen. So to find the likelihood of two events happening, we use the rule of multiplication. There are two rules of multiplication, that is the special and to the general. So as like the same thing which we have discussed in additional. And here the special rule of multiplication here is that requires that two event, let me just have A and B, are independent. So two events are independent if the occurrence of one event does not alter the probability of occurrence of the other event. So there I just want to specify that is independence is the occurrence of one event has no effect on the probability of the occurrence of another event. So one way just to think about independence is to assume that event A and event B are different times. For an example, when event B occurs after event A occurs, does have any effect on the likelihood that event B occurs? No. If the answer is no, then A and B are independent event. So to illustrate independence, suppose two coins are tossed. The outcome of a coin toss, how come it will be? Maybe head or tail. Is it unaffected by the outcome of any previous coin toss? That is also. So here for two independent event A and B, the probability that A and B will both occur is found by multiplying the two probabilities. So this is special rule of multiplication and is written symbolically as like here you can just say P of A product with the P of B. And if you have three independent events, you can just go for A and B and C. Here it would be product of probability of A, probability of B and probability of C. So the special rule of multiplication used to determine the probability that all three events will occur. That is what here comes. And let me just have a discussion on general rule of multiplication. Yes, dear friend, if two events are not independent, okay, if two events that are not independent, they are referred to as dependent. Okay, here I just want to specify a dependency. Okay, so to illustrate a dependency, say let me just have, suppose they are 10 cans. Okay, so of this exact 10 cans, let me have 7 as 7 cans, okay, 7 are regular and 3 are diet can. Okay, diet soda. Okay, a can is selected from this 10. Okay, a can is selected from this 10, and kindly just see the probability of selecting a can of a diet soda. What would be 3 by 10, and the probability of selecting a can of a regular soda, that it would be 7 by 10. And here then if I just want to check for it, then a second can is selected from a cooler without returning the first one. What would be? So the probability the second is diet depends on whether the first one selected was diet or not. Here the probability that a second can is if I am just selecting a diet can. Kindly just observe one such a case. If the first can is diet and second is also a diet, here it would be as like 2 by 9 because already first event happened. So first event happens, here second can I am just having. In that second, if it is already previous the first event, if it is an already a diet, only 2 cans of diet soda remaining in the cooler. So here it would be 2 by 9. And if it's so, the first one would be a regular. What would happen now? It would be 3 by 9. So here this exact fraction, whether it is 2 by 9 or 3 by 9, is aptly called the conditional probability, because its value is conditioned on dependent on to that previous, that is whether a diet or a regular soda was selected first from the cooler work. So that is specified, that is as like a dependent. And dear friends, we use this general rule of multiplication to find the joint probability. Okay, so joint probability of two events when the event are not independent. So for an example, event D occurs after event A occurs, and A has an effect of the likelihood that event B occurs. So in such a case, here the general rule of multiplication states that for two events, if it is A and B, the joint probability that both event will happen is found by multiplying the probability that event A will happen by the conditional probability of event B occurring given that A has occurred. So symbolically the joint probability is found, that is also has been given. Okay, and here the rule of multiplication is specifying like this. Okay, so I think you are able to understand how this calculation is happening. And next I just want to specify this Bayes theorem. Dear friends, this exact Bayes this word is exactly comes it is after this 18th century. Thomas Bayes, an English Presbyterian minister, okay, so actually he made a question, that is, does God really exist? Being interested in mathematics, he attempted to develop a formula to arrive at the probability God does exist based on evidence available to him on earth. So later, Pierre Simon Laplace referred this Bayes work and gave it the name Bayes theorem, and in a workable form as like here, this is what the Bayes theorem specifying, that is assuming as like an formula that event A and event B are mutually exclusive. Or here if we just have a number of event A1 or A2, if we just specify that the event A1 and A2 are mutually exclusive and collectively exhaustive, and here we are referring AI, that is refers to either A1 or A2, which we specified, and hence A1 and A2 are in this case complements. The meanings of the symbol here, it is specified, yes, Okay, the meaning of specifies that, yeah, by an example. So let I just give you a small example. If we let me just have it. Okay, here it is an example. Okay, suppose here 5% of a population, okay, of an woman, here it is specified, that is after fictional this third world country, okay, have a disease that is peculiar to that country. So we will let A1 refer to that event, that is that individual has a disease, and A2, this exact event does not have the disease. So here it is specified 5% of the population. So here 5% of the population as it's specified, yes, that we know that if we select a person from a woman at random, the probability the individual chosen has disease as like 0.5, or towards this P of AI maybe. Okay, so here also we can just, so here when we just say maybe individually can have disease. So here the probability of A of 1 has disease is specified as like a 0.1. So this is specified as like a prior probability. So it is given this name because the probability is assigned before any empirical data are obtained. Okay, now we have this probability, prior probability, and a person is not affected with the disease. Therefore, so here it just comes 0.95 because it is from the complement 1 minus 0.5. Here we just get 0.95. Okay, so that is a diagnostic technique to detect the disease, but it is not very accurate. Okay, now here let this B denotes the event. Test shows the disease is present. Assume that historical evidence shows that if a person actually has the disease, the probability that test will indicate the presence of the disease is 0.9, and using the conditional probability, yes, of course, this exact statement is specified, yes, shows the individual has the disease and it is correct. And here assume the probability that exactly, see 0.15, that for a person who actually does not have the disease, the test will indicate the disease is present. Okay, actually does not have it, but the test indicates yes, the disease is present. So for that it is B and towards A2. And here let's randomly select a person from a woman and perform the test. The test results indicates the disease is present. Okay, what is the probability? The person actually has the disease. What is the probability that the person actually has the disease? Yes, in symbolically we have to specify it is as like A1 towards this B. And kindly just have a note of it, dear friends. This exact probability, it is based on this information added to it after this. So it is specified as like posterior probability. And this one, it is an additional information. And yes, dear friend, with the help of this Bayes theorem, we can calculate, we can determine this posterior probability. And kindly just observe. So the probability that a person has a disease, given that he or she, okay, tested positive is 0.24. How this result interpreted? Yes, if a person is selected at random from the population, the probability that he or she has the disease is 0.5. If the person is tested and the test result is positive, the probability that a person actually has the disease is increased about 5-fold from 0.05 to 0.24. So in the preceded problem, we have only two mutual exclusive and collectively exhaustive. If we just have more than an event, as like A1, A2 till AN. Yes, of course, dear friends, here it just has A1, A2 till for that only we are just specifying this as like AI. Okay, so with this notation we are able to identify, yes dear friend, the event A, that is disease, yes, A1, no disease A2, and here we have the prior probability as like P of A, and towards conditional probability P of B and AI with the both thing, having one more joint probability added with an information of posterior probability. Yes, we are able to observe that what is the resultant of it. Okay, so with this notation, the calculation for the woman problem are summarized as like this. Okay, yes, let me just have this multiplication formula. Dear friend, actually multiplication, that is actually here we are just going to have as like counting, the principle of counting. If the number of possible outcome in an experiment is small, it is relatively easy to count them. As we have already know, for rolling a dice, yes, 6 probability possible outcomes only. What would be 1, 2, 3, 4, 5 and 6? So resulting from the roll of this, here, if within the same case, if however there are large number of possible outcomes, such as number of heads or the tails of an experiment of a 10 toes, if we just make it, or if it would be tedious to count if I just having only one coin, 1 and 2, maybe head and tail, or if we make it as like a 10 times if we tosses, it would be tedious to count all the possibilities, no probabilities, right? So they could have all heads, 1 heads and 9 tails, or 2 heads and 8 tails, and so on. To facilitate counting, yes, we are going to here discuss importantly 3 different formulas. The first formula here, it is multiplication formula. That is not to be confused with the multiplication rule, okay? Earlier we have done it. This is multiplication formula for making the principle of counting. And next one, it is permutation and combination. Yes, first of all, let me just have this multiplication. Here, dear friends, I just want to specify one among the thing. First of all, what is this multiplication is, if I just want to have, if there are, as here it is already specified, if there are m ways of doing one thing and n ways on doing the other thing. So what is the number of way on doing the both? Yes, producting it with m and n. So total number of arrangements, here we have to product the m and to that n count. So this can be extended with to be more than 2 events like that. If you are having m, n and if you are having p event, or if you are having q event. So it is m into n into q, like that. Okay, now let I just make it illustration with a small example. See, actually an automobile dealer having an advertisement, that is you can buy a convertible, okay, a convertible car, okay, that is a 2-door sedan or a 4-door model with your choice of either wire wheel color or solid wheel covers. Okay, so 2-door is there, 4-door is there, and with the covers as like wire wheel cover or solid wheel cover. So here, what would be the, how many different arrangements of models and the wheels can be? Of course, here it is very easy to determine that is total number of arrangements. By this, kindly just observe here, it is not much difficult to count all the possible models and wheel cover combination. See here, convertible with wire car, this is 2-door, okay, and this is convertible with it solid wheel covers, okay. If it is 2 doors, if it is 4 doors, 2 doors wire car, 2 doors solid car, and 4 doors with wire car, 4 doors with solid wheel, that is for solid covers, okay. So kindly just suppose, however, the dealer decide to offer 8 more models. So many things are there, na? Yes, kindly just see here. In such a case, here we are able to make it towards the dealer offer. We are getting M into N, and yeah, it is resulting with 3 into 2, 6 possible arrangements are there. And even if we are having more number of models or more number of types of covers, yes, it would be tedious towards the picture. Or if I just want to frame it, make it last like a picture, it is very tedious. But instead, if you apply it as like a multiplication formula, okay, I just take it towards the point. Yes, 8 models is there, and 6 types of covers is there. Simple, 8 into 6. So totally 48 possible arrangements are there. So kindly just, dear friends, note in the preceding application of multiplication formula that there were 2 or more grouping from which you made selection. And this automobile dealer, for example, offered a choice of model and a choice of wheel covers. If a home builder offered you 4 different exterior style of home to choose from the 3 interior floor pans and multiplication for, how would be used? Yeah, each and everything you can just multiple. Simple thing. But kindly just have what is the number of models, what is number of the arrangements you are getting as like an outcome. There are so many examples it's there, dear friend. Okay, just moving on to the next one. Yes, permutation. As noted, the multiplication formula is applied to find a number of possible arrangements for 2 or more groups. Okay, so here the permutation formula is applied to find the possible number of arrangements when there is only one group of objects. So here, let me have here one more illustration I have just done. So see, 3 electronic parts are to be assembled into a plug-in unit for a television. Okay, so the parts can be assembled in any order. How many different ways can the 3 parts be assembled? Kindly just observe. Here I am having 3 parts. Okay, and here I am having 3 components. And kindly just observe. I am going to make it in order. So one order for this illustration might be the transistor first, or the LED second, and the synthesizer third. And next, maybe anything. Okay, so here the transistor first, this is LED and synthesizer. Next one, transistor is second, LED is first, and synthesizer is third. So in this manner, what would be the number of arrangements? So here, dear friends, note that these arrangements of A, B, C or BAC are different. Both are different because the transistor here it is firstly arranged, but here it is secondly arranged. Okay, anyhow, here the transistor is firstly arranged, but not the second one. It is not LED here. The second one, it is synthesizer. So this exact arrangement is not equal to this arrangement. So that is specified as like a permutation. And here towards the permutation, the exact formula is n factorial. Of course, you all always known about this factorial. Yes, that is we solve the 2 problems. Note that permutation and combination, which we are just going to discuss it later. Here we just use this factorial concept. Okay, so here towards this factorial concept, if I just have assembling in 3 ways and having the 3 parts, yes, here it just comes as like 3 factorial divided by 3 minus 3 the whole factorial. And one important thing, dear friend, kindly just to see by this definition, yes, 0 factorial, it would be equivalent to 1. Okay, so 0 factorial, it is equal to 1. So here 3 factorial divided by 1, that is gives us 6. Okay, so here, yes, dear friends, the 6th way in which the 3 electronic parts, which I have just specified as like an ABC, that has totally arranged in 6 manner. Now next, the combination. Okay, so another counting formula. See, if the order of selected object is not important, any selection is called combination. Here the formula to count the number of R here, yes, kindly just have a note of it. The R object combination from a set of n object. Yes, I have to specify like this. Okay, so these are the two things. And if you are just going to say, have the same thing related with an example as like 3 employees, okay, to 3 employees to work as in concession stand each evening. Okay, there are 7 employees available to work. How many different teams can be scheduled? So here among this each and every team, it has 3 and totally of 7 employees. Yes, here we have the combination of 7 factorial divided by 3 factorial, which is producted with n minus r. Kindly just observe n minus r. So here we just get it as like 35 arrangements. Okay. And yes, dear friend, next we are just going to discuss about probability distribution. See, a probability distribution gives the entire range of values that can occur based on an experiment. Okay, a probability distribution is similar to a relative distribution. Previously we have already given this example. Okay, so relative frequency distribution. However, instead of describing past, it would be a likely future event. That is what probability distribution. Okay, so what is probability distribution? See, a probability distribution shows the possible outcomes of an experiment and the probability of each of these outcomes. And here I have just specified that is a listing of all outcomes of an experiment and the probability associated with each outcomes. And kindly just have a note, dear friends, these are the major characteristic of probability distribution. Yes, the probability of a particular outcome is between 0 and 1. We have already discussed, and outcomes are mutually exclusive. Okay, so what are all the outcomes are there? Mutually exclusive events, and the list is exhaustive. So the sum of the probability of various events, it would be equal to 1. Okay, how can we generate a probability distribution? Let I just explain with the same concept. Okay, so suppose we are interested in a number of head showing face up on 3 tosses. Okay, so here I am just specifying 3 tosses. So this is an experiment. The possible results are, okay, first of all, 0 heads, only 1 head. Okay, here it is 1 head, 2 heads and 3 heads. What is the probability distribution of number of heads? Yes, of course, that is what we want. And kindly just have a note, dear friend, there are 8 possible outcomes. There are 8 possible outcomes. That is, a tail might appear face up on the first toss. Okay. Another tail on the second. Another tail on the third. Or we might get a tail and a head. Both the things are there. And in that order, we can just, so how many? Of course, kindly just make use of it. Yes, according to this counting, there are 2 of 2 of 2. So totally we just have 8 possible results. That is what here we just got it. And with this 8 possible result, kindly note that the outcomes, that is 0 heads, occur only once. And 1 head occurs 3 times. And 2 heads also occurred 3 times. 1, 2 and 3. Okay. And kindly just have a note, dear friend, and the outcome, that is 3 heads, occurred only once. And that is 0 heads appeared 1 out of 8 times. Thus the probability of 0 head is 1/8. Okay, 1/8. And here the probability of that head, 1 head, is 3/8. That is what, so on you can just have it. And yes, kindly dear friends, because of this, 1 outcomes must happen, and the total of the probability of all possible event, that is 1. How this is going to happen? Yes, kindly I explained here. So see here, if I am just having zeroth possibility, that is 0 heads, it is 1/8, and for 1 head it is 3/8. And yeah, when on just summing up, yeah, we already know, yes, the probability, total of the probability of all possible event is 1. This is always true. Okay, so and making it towards this particular, if we are writing the probability of x as the event, that is we are just taking p of x. Okay, so the probability of 0 heads is p of 0 heads, that is 0.125, and the probability of 1 head, we just have 0.375. So all this we just get it. And when having the sum of these mutually exclusive, yeah, we are having this distribution. And yes, in any experiment of chance, the outcomes occurs randomly. So it is often called a random variable. For an example, rolling a single die is an experiment. Any one of the 6 possible outcomes can occur. Some experiment results in outcome that are that is qualitative, maybe such as like dollars or weight or number of children, or other results in quantitative. Okay, so other results in qualitative, such as like any colors or anything as like towards religious preference. Or each values of this random variable is associated with a probability to indicate the chance of a particular outcome. Okay, anything. Here one of the example is like if we count the number of employees absent from the day shift on Monday. So the number of might be 0, 1, 2, 3 like that. So here the number absent is the random variable. Okay, and yes, dear friend, here there are 2 types of random variables is there. One is discrete, and the next one it is continuous. And here the discrete random variable can assume only a certain number of separated values. If there are 100 employees, which we just seen previously, so here I am just mentioning the count is 100 employees. Then count the number of absent on Monday can only be 0 to 100. 0 to 100. Yes. So a discrete random variable is usually the result of counting or result of counting something. Okay. And yes, dear friend, a discrete random variable can in some cases assume fractional or decimal values. Okay. So these values must be separated. That is has a distance between them. Okay, and next it is all about continuous random variable. Yes, on the other hand, if the random variable is continuous, then the distribution is a continuous probability distribution. So if we measure something such as the width of a room, a height of a person, or a pressure in an automobile tire, or the variable that is a continuous random variable. So it can assume one of the infinitely large number of values. So within a certain limitation, kindly just keep that in mind. So here if I just want to specify something as like an example. So yes, a time of commercial flight between Atlanta and Los Angeles, or maybe 4.67 to 5.13. Okay, and so on. So the random variable is the time in hours. Okay, yes, dear friends, so here in this session we have laid a strong foundation in understanding probability and its various aspects, that is essentially for delving deeper into statistical analysis. If you have any questions or need further clarification, feel free to specify it in comment box. And yes, dear friends, looking forward to our next session on discrete and continuous probability distribution. Yes, happy learning, dear friends. Thank you.